In this video series, we will discuss how to solve projectile motion problems. If you find that these video explanations move too slowly, you can use the solutions document to supplement or replace the video explanations. And you can use the table of contents in the progress bar to skip to particular topics in the video. Now let's try our first projectile motion problem. Please pause the video and try this problem. Now, let's discuss the problem together. Here's a summary of the solution for the problem. Now let's discuss the solution step by step. Here are some YouTube controls which you may find useful while you're watching the videos. Projectile motion occurs when the only force on the object is the force of the Earth's gravity. After it leaves the cannon and before it hits the ground, the only force on the cannonball will be the force of the Earth's gravity. So, the cannonball will undergo projectile motion. So to solve this problem, we plan to apply the projectile motion problem-solving framework to the cannonball. Here's a handout which summarizes a step-by-step method for solving two-dimensional projectile motion problems. There's a link to this handout in the video description box. You should print out this handout so that you can follow along with the steps as you proceed through the video. Draw the object's path of motion. For two-dimensional projectile motion, the path is a parabola. You should build as much kinematics information as possible into your sketch. For example, build any given distance information into your sketch. The problem tells us that the cannonball lands at a horizontal distance of 41 meters from the cannon. Build that information into the sketch, like so. Label the key points in time in your sketch. Let's call the instant when the cannonball leaves the cannon t sub 0. In this problem, t sub 0 is the instant when the cannonball begins to undergo projectile motion. When solving physics problems, the standard simplifying assumption is that t sub 0 equals the number 0. So, let's set t sub 0 equal to the number 0. Let's call the instant when the cannonball hits the ground t sub 1. In this problem, t sub 1 will be the instant when the cannonball stops undergoing projectile motion. Choose your axes. For projectile motion problems, it's usually best to choose right and up as the positive directions for your x and y axes. Always write down your axes. Choose an origin for measuring position. It's usually best to choose an origin located at the furthest left x-coordinate and furthest down y-coordinate of the object during the interval of projectile motion. This is the furthest left x-coordinate of the cannonball during the interval of projectile motion, and this is the furthest down y-coordinate of the cannonball during the interval of projectile motion. So let's choose this point as the origin. The origin is the point at which the x and y coordinates of the position are both 0. Always label your origin. This point would be a poor choice for the origin because the cannonball will not be located this far left during its projectile motion. Label the coordinates for position for each of the key points in time in your sketch. Always try to use the exact right symbols, including the exact right subscripts. At t sub 0, the coordinates for the position are x sub 0 and y sub 0. At t sub 1, the coordinates for the position are x sub 1 and y sub 1. When possible, write down a specific value or symbol for each coordinate. This position has the same horizontal location as the origin, so x sub 0 equals 0. This position is located at a vertical distance of h above the origin, so y sub 0 equals h. This position is located at a horizontal distance of 41 meters to the right of the origin. So, x sub 1 equals 41 meters. This position has the same vertical location as the origin. So, y sub 1 equals 0. Identify the question with a question mark. When convenient, represent what the question is asking you for with a symbol. When convenient, build the question into the sketch. In this problem, the question asks us to determine the value of h. So, we can represent what the question is asking us for with the symbol h, and we can build that question into the sketch, like so. Remember that we decided that y sub 0 equals h, so we can also say that the question is asking us for y sub 0. The problem tells us the velocity at time 0, so let's draw that velocity vector. The direction of the velocity vector at a particular point in time represents the object's direction of motion at that point in time. So, the velocity vector at a particular point in time is drawn tangent to the object's path of motion at that point in time. So, the velocity vector at time 0 is drawn tangent to the object's path of motion at time 0. Tangent to the object's path of motion at time 0, like so. You should know that a vector is a concept that has both a magnitude and a direction. You should know that a magnitude is a number that can be positive or 0, but that can never be negative. The concept of velocity is a vector, so velocity has both a magnitude and a direction. For this problem, the magnitude of v sub naught is 20 meters per second. The symbol v sub naught, written without an arrow on top, stands specifically for the magnitude of the velocity vector. The direction of the velocity vector at time 0 is represented by an angle of 35 degrees upward from the horizontal. We can build that information into the sketch like so. A vector can be broken into components. Components are a way of representing a vector relative to your axes. To solve physics problems, we usually need to work with vector components rather than with overall vectors. So, to solve a kinematics problem, we need to break the velocity vector into components. In order to break the velocity into components, we will need to draw a right triangle and apply the SOHCAHTOA equations. Here's a summary of the method for breaking the velocity into components. Now let's discuss this process step by step. Remember, if you thought it was easy to break the velocity into components, you can use the table of contents in the progress bar to skip to the next topic in the video. We begin by redrawing the velocity vector. Now we need to draw a right triangle. The overall vector will form the hypotenuse of the right triangle. The legs of the right triangle should be parallel to your x and y axes. We've chosen horizontal and vertical axes, so we draw a right triangle with horizontal and vertical legs. The legs will represent the components of the velocity. Label the sides of the right triangle. The hypotenuse represents the overall velocity vector. This leg is parallel to the x-axis, so this leg represents v sub 0 x, the x component of the velocity at time 0. This leg is parallel to the y-axis, so this leg represents v sub 0 y, the y component of the velocity at time 0. As we will discuss later, in projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. So we can use the symbol v sub x to stand for the horizontal velocity at any point during the projectile motion. The vertical velocity is changing, so we must continue to use the symbol v sub 0y to indicate that this component represents the vertical velocity only at time 0. Always try to use the exact right symbols, including the exact right subscripts. The overall velocity vector points up and right. So the y component of the velocity points up, and the x component of the velocity points right. Right is our positive x direction, so v sub x is positive. Up is our positive y direction, so for this problem, v sub 0y is also positive. I label the 35-degree angle with an asterisk to indicate that we plan to use this 35-degree angle in our SOHCAHTOA equations, rather than using this 55-degree angle. Label the sides of the triangle. This side is labeled hypotenuse because it's across from the 90-degree angle. This leg is labeled adjacent because it's adjacent to the angle we marked with the asterisk. This leg is labeled opposite because it's opposite to the angle we marked with the asterisk. Now, we're ready to write the SOHCAHTOA equations. Which of the SOHCAHTOA equations should we write? In this case, we know the length of the hypotenuse, so we want to use the two equations that include the hypotenuse. So, we will write the equations for sine and for cosine. The tangent equation doesn't include the hypotenuse, so the tangent equation would be less useful in this case. First, we write the general SOHCAHTOA equations. The memory aid SO tells us that sine equals opposite over hypotenuse. The memory aid CA tells us that cosine equals adjacent over hypotenuse. Now, we can plug in specifics. The length of the hypotenuse represents the magnitude of the overall velocity vector at time 0, which we know is 20 meters per second. The length of the adjacent leg represents the magnitude of v sub x, which we can represent with the symbol v sub x written inside absolute value signs. The length of the opposite leg represents the magnitude of v sub 0y, which we can represent with the symbol v sub 0y written inside absolute value signs. This equation now has one unknown, and this equation now has one unknown. So we can solve this equation for the magnitude of v sub 0y, and we can solve this equation for the magnitude of v sub x. Our results are that the magnitude of v sub 0y equals 11.5 meters per second, and the magnitude of v sub x equals 16.4 meters per second. We use absolute value symbols in our SOHCAHTOA equations because the SOHCAHTOA equations can only tell us the magnitudes of the components. It's our job to determine the plus or minus sign for each component in a separate step. We decided earlier that v sub x is pointing in the positive x direction, and that v sub 0y is pointing in the positive y direction. So v sub 0y and v sub x are both positive. One of the most common student mistakes is forgetting to include negative signs in front of negative components. So, I recommend that you should make it a habit to include plus signs in front of positive components, like we did here and here, because that will help you to remember to include the crucial negative signs in front of negative components. Always try to use the exact right symbols. When you're dealing with an overall vector, a symbol written with an arrow on top stands for the complete vector, including both magnitude and direction. A vector symbol written without an arrow on top stands specifically for the magnitude of the vector. So, here I write the symbol v without an arrow on top, because this equation refers specifically to the magnitude of the velocity vector, 20 meters per second. When you're dealing with vector components, a component symbol like Vx or Vy represents the complete component, including both the magnitude and a plus or minus sign to represent the direction. In contrast, the absolute value of the component stands specifically for the magnitude of the component, without a plus or minus sign. In this line, I wrote the component symbols inside absolute value symbols to indicate that this line represents the magnitudes of the components. On the other hand, in this line, I wrote the component symbols without absolute value signs to indicate that this line represents the complete components, including both the magnitudes and, in this case, plus signs to indicate the directions of the components. I discussed the process for breaking vectors into components in detail and gave several examples in my earlier video series on vector components. There's a link to that series in the video description box. Build your results for the vector components into the sketch, like so. Choose the 2 points you will treat as the initial and final points in your kinematics equations. The initial and final points are defined as the 2 points that we plan to substitute into our kinematics equations. For this problem, we plan to substitute t sub 0 and t sub 1 into our kinematics equations. So we need to label those 2 points with an I and an F. Here's a summary of the steps we completed in order to build as much kinematics information as possible into our sketch. Now we write down the projectile motion setup. The purpose of this setup is to organize the kinematics data. In projectile motion, the downward force of gravity creates a constant downward acceleration with magnitude 9.8 meters per second squared. This downward acceleration causes the object's vertical velocity to change at a rate of 9.8 meters per second squared. So, in projectile motion, the vertical acceleration is constant, and the vertical velocity is changing. The kinematics variables for constant acceleration and changing velocity in the y component are delta t, y initial, y final, v initial y, v final y, and a sub y. Don't confuse velocity with acceleration. The symbols v initial y and v final y take it for granted that the vertical velocity is changing. That's why we need separate symbols for the initial vertical velocity and the final vertical velocity. The symbol a sub y takes it for granted that the vertical acceleration is constant. That's why we can use the single symbol a sub y to refer to the acceleration at any point during the interval of projectile motion. In projectile motion, there are no horizontal forces on the object. So, the object's horizontal acceleration is 0. So, the horizontal velocity is constant. The kinematics equation for constant velocity motion in the x component is x final equals x initial plus v sub x delta t. The symbol v sub x takes it for granted that the horizontal velocity is constant. That's why we can use the single symbol, v sub x, to refer to the horizontal velocity at any point during the interval of projectile motion. Don't confuse the horizontal velocity, which is constant, with the vertical velocity, which is changing. Think in terms of components. In projectile motion, the setup for the vertical component is different from the setup for the horizontal component. The setup for the horizontal component is to write down this kinematics equation. In contrast, the setup for the vertical component is to list these 6 kinematics variables. The one variable that appears in the kinematics setup for both the x and the y component is delta t. So, delta t forms the connecting link between our kinematics setup for the x component and our kinematics setup for the y component. We expect to use one of the components to determine delta t, then substitute our result for delta t into the kinematics setup for the other component. Arrange your setup for the x component and your setup for the y component in 2 adjacent columns. The key to succeeding with projectile motion problems is to use this projectile motion setup. So, please pause the video and memorize this setup for projectile motion. In your setup, indicate the question with a question mark. The question is asking us for the value of h. We've determined that y initial will equal h. So we write a question mark above y initial, and underneath that we write the more specific symbol h. So our plan is to use the kinematics equation for the x component to determine delta t. Then we will substitute our result for delta t into our setup for the y component. Then we will use a kinematics equation for the y component to determine h. In your projectile motion setup, underneath the general variables, write down a specific number or symbol for each variable. Based on the work we did in our sketch, we substitute 0 for x initial and h for y initial. We substitute 41 meters for x final and 0 for y final. Based on these results, which we obtained when we broke the initial velocity into components, we can substitute positive 16.4 meters per second for v sub x, and we can substitute positive 11.5 meters per second for v initial y. For v final y, we can substitute the more specific symbol v sub 1y, which stands for the y component of the velocity at time 1. Now, sometimes students wrongly think that v sub 1y should be 0, since the package will be motionless after it hits the ground. But since we're planning to substitute these variables into our projectile motion equations, we should think of v sub 1y as the last instant that the package is moving through the air, rather than as the first instant that the package is resting on the ground. So we should not substitute 0 for v sub 1y. For delta t, let's continue to use the symbol delta t. For projectile motion problems, if we choose up as our positive y direction, then a sub y is negative 9.8 meters per second squared. 9.8 meters per second squared is the magnitude of the acceleration due to the Earth's gravity. The force of the Earth's gravity pulls down, so for projectile motion problems, a sub y points down. Since we chose up as our positive y direction, a sub y is negative. This negative sign is crucial. If you leave out this negative sign, you will get the problem wrong. The key to succeeding with projectile motion problems is to create a careful projectile motion setup for each problem. The purpose of the setup is to organize the kinematics data that you will need to solve the problem. Please pause the video and study how we came up with this setup for this problem. Here's a summary of the steps involved in creating the projectile motion setup. Now we're ready to work with the kinematics equations. Because the y component for projectile motion deals with constant acceleration and changing velocity, there are 3 different kinematics equations to choose from for the y component. When you know values for 4 of the variables in your setup for the y component, you're ready to choose a kinematics equation for the y component. So far, we only know 3 values for the y component, so we're not ready yet to choose a kinematics equation for the y component. Because the x component for projectile motion deals with constant velocity motion, for projectile motion problems, we always use the same equation for the x component. X final equals x initial plus v sub x delta t. In our projectile motion setup, we substituted values for x final, x initial, and v sub x. So there's only one unknown left in this equation, delta t. So we're ready now to solve this equation for delta t. Our result is that delta t equals 2.5 seconds. We substitute the result for delta t that we determined from the x component into the kinematic setup for the y component. When you know values for 4 of the variables in your setup for the y component, you're ready to choose a kinematics equation for the y component. We do now know values for 4 of the kinematics variables for the y component. Delta t, y final, v initial y, and a sub y. So we are ready now to choose a kinematics equation for the y component. The quickest way to choose a kinematics equation is to identify the kinematics variable that we do not care about. We care about these 4 variables because we know their values. And we care about y initial because that will tell us the answer to the question. So for this problem, the kinematics variable that we don't particularly care about is v final y. So let's choose the kinematics equation that's missing v final y. Let's choose the kinematics equation that's missing v final y. That's this equation. First, write down the general equation. Y final equals y initial plus v initial y delta t plus 1/2 a sub y delta t squared. Now, we can use our kinematics setup to plug specifics into the equation. Notice that here and here we use our result for delta t that we determined from our work on the x component. Be careful to include this crucial negative sign when you substitute negative 9.8 meters per second squared for a sub y. And don't forget that we need to square this number. Our kinematics equation now has one unknown, so we can solve this equation for h. Our result is that h equals 1.88 meters. For a 2-dimensional projectile motion problem, I recommend that you should arrange your work for the x component and for the y component in 2 adjacent columns, like we've shown here, because that will help you to keep your math organized. We should build our result into our sketch, like so. We can also build our result for delta t into our sketch, like so. Now we're ready to answer the question. The question asked us for the value of h. Let's round our answer to 2 digits, so that our final answer is h equals 1.9 meters. Here's a summary of the final steps in our projectile motion process. Actually, we have one more check left to make. We should check that our results make sense. Does it make sense that our result for delta t is positive? Well, delta t stands for the time elapsed. Time elapsed can never be negative, so yes, it does make sense that our result for delta t is positive. Does it make sense that our result for h is positive? Well, h stands for the cannonball's height at time 0. It wouldn't make sense for the height to be negative. So yes, it does make sense that our result for h is positive. Does the size of our result for h make sense? Well, if you're more used to using yards and feet in everyday life rather than using meters, then it will be helpful to know that 1 meter is roughly 1 yard, and 1 yard is 3 feet. So, 1.88 meters is roughly 2 yards, or 6 feet. I would say that yes, a height of 2 yards, or 6 feet, for the mouth of a cannon does make sense. Now let's do a recap of our work on this problem. In this video, we learned a step-by-step method for solving projectile motion problems. The key to this method is to write down the projectile motion setup, as we've shown here. To succeed with projectile motion problems, think in terms of components. The problem told us that the cannonball has an initial velocity with magnitude 20 meters per second. So let me ask you a question. Where did we plug the number 20 meters per second into our kinematics equations? Here's the answer. We did not plug 20 meters per second into our kinematics equations, because 20 meters per second represents the magnitude of the overall velocity vector. Instead, we broke the 20 meters per second into components, and then we substituted each of those components into the kinematics equations. Make sure that you understand the SOHCAHTOA process we used for breaking the initial velocity into components. Remember that I have another video series that focuses on the process for breaking vectors into components. You should make it a habit to include a plus sign in front of positive components, because that will help you to remember to include the crucial negative signs in front of negative components, such as a sub y for this problem. In projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. So, for the horizontal velocity, we use the single symbol v sub x. But for the vertical velocity, we need to use two symbols, v initial y and v final y. And we need to use a different setup for the horizontal component of projectile motion than for the vertical component of projectile motion. For a projectile motion problem, the connecting link between the x component and the y component is delta t. To solve the problem, we expect to use one component to find delta t, then substitute our result for delta t into the setup for the other component. Arrange your work for the x component and your work for the y component in two adjacent columns. For a projectile motion problem, build as much kinematics information as possible into your sketch. When convenient, build the question into the sketch. Draw a large sketch so that you'll have ample room to clearly include all the information you need in your sketch. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.